Hey everyone, welcome to part 2 of our friction unit. And so hopefully you've had a chance just to kind of get a kind of brief understanding or an idea of what friction is. So we can determine the amount of frictions as we start to move into some of this, the mathematical concepts here that exist between two surfaces that are in contact. And so this can be done by defining the force of friction and the weight of an object as a ratio. This value, and is one that we're going to be using, is called the coefficient of friction. Now this coefficient of friction kind of looks like the letter U, but it has two little tails coming off of it. It's a Greek symbol, and it stands or said as mu. Okay, the Greek letter mu, which really just looks kind of like a U with two tails coming off of it. So its ratio is the force of friction divided by the normal force. It's also, and I should kind of add in here that the coefficient of friction is also a magnitude only, and so it's not a vector, which means it does not indicate direction. So when we take a look at the force of friction and the normal force, in terms of calculating the coefficient of friction, really all we're going to be doing is taking a look at the magnitude of the force of friction and the magnitude of the normal force, and that will help us calculate the coefficient of friction. And so we can also have a couple of different spots for coefficient of friction. We can have, or a couple of different equations. So you can see here that we have two separate formulas that are the same thing as our original formula with slight changes to them. We have S and K, whereas S just stands for static from before. Remember, static just means still, so it's the equation that we would use here is when we have objects that are not moving. And then we have our other coefficient of friction, which is kinetic, which is the formula that we would use when objects are moving, and just kind of being accurate with those. So I have a table here that goes through just some different materials and gives you their kinetic friction and their static friction for each one. Obviously, you'd have this table with you on any assessments or anything, and it's not something you'd have to write down somewhere else. I also have a handout sheet for it for those that want to go grab that as well. So we'll come back and reference this kind of throughout some of the activities that are there. So in terms of different problems that we could get, we have three different situations that really arise when we deal with friction. We have objects on a horizontal plane where we have a force applied, pushing something forward, and a force of friction moving directly against that object. And then we have a force of gravity pushing it down. In this case, our normal force is going to be perpendicular to the surface and is going to go straight up. So we have our normal force. Now, what can we take from this? Really, we can take that the force applied is really going to be equal to the force of friction when an object is either in one of two scenarios, either where it's not moving or when we have constant velocity. And those are two kind of very important scenarios that could happen or could pop up. So constant velocity. So if we keep in mind kind of in each of these scenarios, what's happening here if we're not moving or if we have a constant velocity is that acceleration is equal to 0. And if acceleration is equal to 0, then that means that I have no net force. So then the net force is equal to 0. And the only time that can happen is when I have an object that's not moving, or an object with constant velocity, because I have this acceleration that's 0, which means I have a net force that's 0. So in this scenario, if I'm on a horizontal plane, my force applied and my force of friction would be equal to each other when I have these two situations. Similarly, the force of gravity would equal my normal force, and they would oppose each other. And so keep in mind here, because we're going to be using these to calculate coefficients of friction, we're not really so much concerned with direction because the coefficient of friction is just a magnitude. So we're just looking at the ratio between the frictional force and the normal force. But if I knew an applied force that was there, or a force that could just start to get the object to move, then I could make that assumption that that would be equal to a frictional force that would be there. Same thing with the force of gravity. I know the gravity pulls downward and normal force opposes that and goes up. but when we're taking a look for coefficient of friction here, we're really just taking a look at the magnitude, and so we're going to be seeing kind of no directions, just more of a magnitude value. So situation 2 and 3 really start to apply when I have, let's say in this scenario, somebody's pulling a box with a rope, and so maybe they're not necessarily pulling it in line horizontally with the object, but are more, the object's lower than they are, and so they have to pull the object at an angle. And so in that case, we can't just say that the force applied is equal to the force of friction, and we need to kind of assume something else. And so this is actually a problem that we won't encounter this year, but will come up later on. And similarly with problem 3, or situation 3 on ramps, this is where I would start in terms of physics 12 and talking about how objects can move around. And so situation 2 and 3 really apply for later on, but I just want to make you kind of aware that they are there. And we're mostly going to be dealing in situation 1. Just straight horizontal problems, just to get used to the unit and the topic. So I have an example that we'll take a look and we'll work through the solution for. So in example 1, in the horizontal starting area of a 4-person bobsled race, the 4 athletes with a combined mass, including their outfits, of 295 kilograms exert a minimum horizontal force of 41 newtons forward to get the 315 kilogram sled to start to move. So after the sled's traveled for almost 15 meters, all 4 people jump into it, and then the sled experiences a kinetic friction of a magnitude of 66 newtons. And so we need to determine the static friction and the kinetic friction of this problem. So in order to do that, we're going to have to set up our 2 formulas for A and B. So I'm just going to put in a blank page, and we'll start to take a look here and see what we have. So let's take a look at problem A. So A wants us to calculate the static friction, and we have our formula for this. The coefficient of static friction is equal to the force of static friction divided by the normal force. And so the value for static friction in this case, I believe it's 2 values here that we talked about, but we just need to kind of figure out a little bit more on what they are. So I have these people that are pushing this sled, right? So I have a sled, but I have 4 people that are not in it yet. So it's a horizontal problem, and it says that they take 41 newtons. If we go back and just take a look at it, it takes a minimum horizontal force of 41 newtons to move it. So that 41 newtons is a force applied that needs to happen to the minimum value that it just starts to cause it to move. So we know that our force of static friction must be the same as that, just in the opposite direction, because that was the minimum value that was required. So in terms of the force of static friction, that must be the maximum static friction that can be there just before the object starts to move and turn into kinetic friction. So kind of understanding that part, we have this force applied. That's 41 newtons, which means backward, my starting friction, or my force of friction in this case, must also have been 41 newtons going back. Now, we know that the people are not in the sled yet. They're pushing the sled, and so the sled itself weighed 315 kilograms. So we can use that and figure out what the force of gravity must have been on these people. So force of gravity, on the sled. So we have 315 kilograms, and that's going to get multiplied by this negative 9.8 meters per second squared. Force of gravity is equal in this case to 3,087 newtons. And so remember, we're just taking a look at the magnitude. It is going downward, but because we're asked to solve for the coefficient of static friction, we're just looking for the magnitude value of it. And so the force of gravity opposes the normal force moving upward. And so because these objects are in contact, I can make the assumption that the force of gravity is equal to the normal force. So that helps me with one part. This is 3,087. Okay, 3,087 newtons. And then my force of static friction, remember the minimum value to cause it to move is at 41 newtons, so I have that value without any additional calculations. Which means that my static friction, 41 divided by 3087, gives me 0.01328. Notice here that the newtons units canceled out top and bottom. The coefficient of friction is unitless. It's just a magnitude of the ratio between the static friction and the normal force. So if I take a look at significant digits here, we're going to have 2 with the 41, so 0.013. Then if I take a look at B, B is saying, okay, now these people have jumped in the sled, and it's asking for the kinetic friction in this case. So I've got my kinetic friction and my normal force, and so I need to figure out the force of gravity again, because the mass has changed now, because now the people have jumped in this sled. So force of gravity in this case is going to be 610 kilograms, and all I did to get that was take the 315 from the sled and add it together with the 295 for the people, and so I get 610 kilograms for a total mass. So 610 kilograms and divided by the same 9.8 meters per second squared, and so the force of gravity in this case is going to give me 5,978 newtons. And so the second part of this then is plugging it in on our side over here. So remember, I know that Fg is still equal to Fn because these surfaces are in contact. So I've got 5,978 newtons. Now, for a kinetic friction force, if I read the problem again, it says after the sled has traveled for almost 15 meters, all 4 people jump in and the sled experiences a kinetic friction of magnitude 66 newtons. So it tells me what the kinetic friction is. So Fk, in this case, is just equal to 66 newtons. And so I can calculate the kinetic friction, because the kinetic friction would just work out to 2 significant digits to be 0.011. My kinetic friction value is a little bit smaller than my static friction value, which is kind of the something that should always happen because your static frictional value should be a little bit bigger. So let's take a look at one other problem. Let's see if you can get this one on your own. So pause the video, read it through, give it a try, and come back when you're ready. Alright, so a truck's brakes are applied so hard that the truck goes into a skid on this dry asphalt road. And so that's a pretty key piece of information, because really that value, why else would it give it to us if it wasn't in a table somewhere that we could look up a value for it? So if the truck and its contents have a mass of 4.2 times 10 to the 3 kilograms, so it gives us a mass, determine the force of kinetic friction on the truck. So in this case, it's asking for the force of kinetic friction, which we don't know. But we do have this formula, mu k is equal to Fk over Fn, that I can rearrange to solve for Fk. So Fk is really just equal to mu k multiplied by Fn. So they multiply each other to solve for it. So we need to then figure out, okay, a couple different things before we can kind of proceed to figure out what the force of kinetic friction is. The mass of this equals 4.2 times 10 to the 3 kilograms. And so I can use that to find my force of gravity. So my force of gravity, Fg equals mg. Force of gravity is equal to 4.2 times 10 to the 3 kilograms. Gravity is negative 9.8 meters per second squared. So Fg is going to work out to be 41,160 newtons of force being applied. And then we keep in mind that we know that Fg is equal to Fn with their magnitudes, and they're opposite in direction. And so really I know Fn now. All right, I know the magnitude of Fn is 41,160 newtons. Now, if I knew the coefficient of kinetic friction in this scenario, then I'd be able to solve the problem. And so it talks about a dry asphalt road. So if I go back and I take a look at my table, it's talking about a truck moving along on this road. So rubber on the wheels, I have our asphalt road, and it's a dry scenario. Our kinetic friction, 1.07. So I can go back and I can plug that in to my equation and see what we end up with here for a final value. One over. So we know that mu k is 1.07, and we know that the normal force is just equal to the force of gravity, which is at 41,160 newtons, and so the force of kinetic friction is then equal to 41.2 newtons. And remember that we are dealing with a force in this case. It's no longer the kinetic ratios, and we know that the force of kinetic friction is always kind of going backward or opposing the motion of whatever was in whichever direction it was traveling. So as a final value with significant digits put in, our coefficients of friction, they're constant, so they don't really count against us anywhere. So we wouldn't be using those in any of the calculations. Really, we'd be going back to the mass at 4.2 to realize that this thing is 4.4 with two significant digits. So 4.4 times 10 to the 1, 2, 3, 4 newtons going backward. Okay, so your coefficient of friction values, they're not going to count against you in terms of significant digits. Gravity using that constant 9.8 meters per second squared also does not count for significant digits, so because they're constant values. And so we can kind of look at the other pieces of information to then figure out where they would be. But that gives you a bit of an idea on how to calculate coefficients of friction, static friction, in order to maybe move on and be able to work on our next worksheet. So if you have any questions, let me know.